Ever wonder how ancient mathematicians, folks centuries before calculus was even a concept, figured out areas of tricky curved shapes or volumes of complex objects?
It's a fascinating question, isn't it? They had this incredibly clever technique.
Exactly. Today we're doing a deep dive into something called the method of exhaustion. It's this logical approach the classical Greeks developed.
And it's really in many ways the conceptual bedrock for calculus. Our aim here is to unpack the core idea, see how it developed.
And trace that surprising line right up to modern calculus, right?
Precisely. We want to understand the ingenuity behind it, especially since they lacked our modern algebraic tools. Their level of rigor was groundbreaking.
Okay, so for this deep dive, we're looking at various historical descriptions, insights from math history texts, and particularly the work of Eudoxus of Cydus, who seems like a key player.
A major figure, absolutely. So let's get into it. The essence of the method of exhaustion. It's actually quite simple at its heart.
Simple how?
You take a complex shape, say something with a curve, and you approximate it using simpler known shapes, usually polygons.
Okay, like fitting squares or triangles inside.
Exactly. And the key is you use a sequence of these polygons. Think more and more sides.
Ah, so you start maybe with a square inside a circle, then maybe an octagon, then a 16-sided figure.
Precisely. And as you add more sides, these inscribed polygons fill up more and more of the circle. Their properties, like their area, get closer and closer to the circle's properties.
There's a picture like that, figure 1 in A Brief History, showing polygons just increasingly hugging the inside of the circle.
Right. The idea is convergence. The area of the polygon converges to the area of the circle. It's like they exhaust the space between the polygon and the curve.
That term exhaust really fits. I read that Antiphon of Athens way back noticed something like this.
Yes, Antiphon had this observation. He saw that an inscribed square covers more than half the circle's area. Then an octagon covers more than 3/4. And if you keep doubling the sides, a regular polygon with, say, 2 diggly sides covers more than $1 of the area.
Wow, so you can see how that gap gets smaller and smaller very systematically.
It really does. But to make these arguments stick, mathematically speaking, they needed a rigorous proof method.
And that often involves something called, was it double reductio ad absurdum? Sounds intense.
It does sound a bit daunting, but the logic is quite powerful. It's based on a very fundamental principle, the law of trichotomy.
Trichotomy, meaning 3 parts.
Exactly. For any 2 comparable quantities, let's call them A and B, only one of 3 things can be true. Either A is less than B, A equals B, or A is greater than B. That's it.
Makes sense. One of those has to be true.
So to prove that A actually equals B, they used an indirect approach. First, they'd assume A is less than B.
Okay, assume AB.
And then, through logical steps based on their geometry, they'd show that this assumption leads to some kind of impossibility, a contradiction.
So if assuming AB leads to nonsense, A can't be less than B. Got it.
But they weren't done. Then they'd make the other assumption. Assume A is greater than B.
Assume AB, and I bet that leads to a contradiction too.
That's the goal. Show that AB also results in a logical impossibility.
So if A can't be less than B and A can't be greater than B,
The only possibility left standing, the only logical conclusion, is that A must be equal to B.
huh. It's like boxing the truth in by eliminating the alternatives. Very clever.
Extremely clever.
Right.
And this method, the method of exhaustion, it didn't just appear fully formed, it evolved.
Right. You mentioned key figures. Antiphon started it.
Antiphon of Athens, around the 5th century BC, yes. He's really credited with that initial crucial idea. Let's use inscribed polygons to figure out a circle's area.
The historian Heath apparently said Antiphon deserved an honorable place for originating the idea.
And rightly so. It was a fundamental conceptual leap. Then came Bryson of Heraclea.
Okay, what did Bryson add?
Bryson took it further. He thought, why only inscribed polygons? He used polygons outside the circle too, circumscribed ones.
Oh, so squeezing the circle from both sides, inside and out.
Exactly. He grasped that the circle's true area had to be sandwiched between the area of the inner polygon and the area of the outer polygon.
That makes perfect sense. You got a lower bound and an upper bound.
And crucially, he understood that by increasing the number of sides on both polygons, you could make the difference between their areas, the gap the circle sits in, as tiny as you wanted.
That feels very close to the modern idea of limits.
It absolutely foreshadows it. Heath noted this connection to Archimedes' later, more famous work too.
Okay, Antiphon, Bryson. And then the big name, Eudoxus.
Eudoxus of Cnidus, yes.
Yeah.
Around the 4th century BC. He seems to be the one who really transformed these ideas into a properly rigorous, formal mathematical technique.
And he wasn't just a mathematician, was he? Sources say he was into astronomy, medicine, geography, a real polymath.
Indeed. And it's likely his work in other fields, particularly his theory of proportion, was vital.
Theory of proportion. How does that connect?
Well, Greek mathematics had hit a snag with incommensurable quantities, things like the diagonal of a square and its side, whose ratio isn't a simple fraction. Eudoxus developed a theory that could handle these irrational ratios rigorously.
Ah, so being able to compare any two lengths, rational or irrational, was key.
It was essential. And needing that kind of rigor for comparing magnitudes probably pushed him to formalize the method of exhaustion for areas and volumes, too.
And we find his work in Euclid's Elements.
A lot of it, yes. Particularly in Book 12. That book starts using the method of exhaustion right away, with Proposition 12.2.
Okay, Proposition 12.2. What does that state?
It's a classic result. The areas of two circles are proportional to the squares of their diameters. So if you double the diameter, you quadruple the area.
A fundamental property. And Eudoxus proved this using exhaustion. How? Did he need other tools?
Yes, the proof rests on a few key principles already established, mostly within Euclid's system. You need about 4 main things.
All right, what's the first one?
First, something called the axiom of comparability. You might also hear it called Eudoxus's axiom or the lemma of Archimedes.
Okay, what's the gist?
It basically says that if you have two quantities of the same kind, like two lengths or two areas, you can always find a whole number multiple of the smaller one that's bigger than the larger one.
So no matter how tiny one line is compared to another, if you lay enough copies of the tiny one end to end, you'll eventually surpass the big one.
That's the idea. It sounds obvious, maybe, but it formally guarantees you can form meaningful ratios between magnitudes. It only works for magnitudes of the same type, though you can't compare a length and an area this way.
Got it. Axiom of comparability. What's next?
Second, the principle of exhaustion itself. This is actually Euclid's proposition X.1.
Ah, the core idea of formalized as a proposition.
Yes. It says if you start with some magnitude and you repeatedly subtract more than half of what's left, you'll eventually end up with a magnitude smaller than any tiny magnitude you chose beforehand.
So keep taking away more than half, and you can shrink the remainder down below any target, no matter how small.
Exactly. And Boyer pointed out it works even if you subtract at least half, or really any fixed fraction, each time. The key is you're guaranteed to get arbitrarily small.
Okay, that's crucial for making the gap disappear, conceptually. What else?
Third, he needed Euclid 12.1, which relates similar plane figures. It says their areas are proportional to the squares of their corresponding sides.
Like the area of similar triangles relates to the squares of their bases?
Precisely. And fourth, another proposition, Euclid EL.1, which deals with proportional relationships in similar rectangles. It's a bit more technical.
Okay, so a whole toolkit of geometric principles. How did Eudoxus use these with exhaustion to prove the circle area thing, 12.2?
He used that double reductio ad absurdum proof we talked about.
Right. Assume it's false and show that leads to contradictions.
Exactly. He'd start by saying, suppose the ratio of the areas of two circles is not the same as the ratio of the squares of their diameters.
Okay, so the ratio of areas is either bigger or smaller than the ratio of the squared diameters.
Correct. Let's take the bigger case. Assume area 1, area 2 is greater than diameter 1 to diameter 2, 2.
Right.
Now, he inscribes polygons in both circles. Using the principle of exhaustion, X.1, he knows he can make the polygons so close to the circles that the leftover area, the little crescent bits, is smaller than whatever tiny amount is needed to mess up the inequality he assumed.
Okay, so the polygon areas get really close to the circle areas.
Very close. But the polygons are similar figures.
Yep.
So by 12.1, the ratio of their areas is exactly equal to the ratio of the squares of corresponding lines, which relate to the diameters.
Ah, so the polygon areas follow the rule.
But he assumed the circle areas didn't. And by making the polygons close enough to the circles, he forces a contradiction with his initial assumption. The same logic works if you assume the ratio areas is smaller.
Wow, that is intricate. It weaves together the approximation idea, the geometric propositions, and that indirect proof structure.
It's a masterpiece of logical reasoning for its time. There's that illustration, figure 2, showing a segment of a circle. You put a triangle in it. The key insight is that the two smaller segments left over are, together, less than half the area of the original segment.
So each step of adding sides to the polygon, like doubling them, cuts away more than half of the remaining difference.
Exactly, ensuring you exhaust that difference, bringing the polygon area arbitrarily close to the circle area, which is essential for the reductio proof.
It's clear why Eudoxus is held in such high regard. You mentioned Dunham rates him second only to Archimedes.
That's a common view, yes. He provided the rigorous proofs for things that might have been known or suspected earlier.
Like the Babylonians and Egyptians knew that circle areas related to diameter squared, but maybe not why rigorously.
Exactly. They had formulas based on observation or tradition. Eudoxus provided the logical underpinning within the Greek deductive system.
And the name method of exhaustion, you said, that came much later.
Much later, yeah. Coined by Gregory of St. Vincent in 1647. But the method itself is ancient Greek.
Now, despite its brilliance, it wasn't the final word, was it?
No, it definitely had its limits. While powerful, applying it to, say, more complicated curves or volumes could become incredibly complex and unwieldy. Each proof was sort of a custom job.
Lacking a general algebraic framework, maybe.
That's a big part of it. This complexity, this sort of case-by-case difficulty, really created the need for something more powerful, more general.
And that's where calculus eventually comes in.
Absolutely. The method of exhaustion is like the ancient ancestor. It embodies the core idea of a limit approaching a value by getting infinitely close, which is central to integral calculus. That's why ancient calculus roots is such a fitting title for our chat.
It really demonstrated the concept even without the notation.
Precisely. It was the crucial stepping stone. And, it connects to an interesting ongoing discussion about what mathematical rigor even means.
How so has the definition changed?
You could say that. Some modern analysis points out that Greek geometry, including Archimedes' use of exhaustion, relied on some assumptions that weren't explicitly stated as axioms back then.
Like what kind of assumptions?
Things we take for granted now, maybe, like the idea that every reasonable shape has a definite positive area, or that if you cut a shape up, the areas of the pieces add up to the area of the whole, or that shapes that are identical in size and form, congruent, must have the same area.
Those seem pretty fundamental. Were they just considered obvious?
Largely, yes. They were part of the intuitive understanding of geometry. So the argument goes, if you add these unstated assumptions as explicit axioms to the Greek system, then their proofs, like those using exhaustion, are rigorous by their own standards and even quite close to ours.
But our modern standards demand we state all our starting assumptions up front.
Exactly. The bar for what constitutes a fully rigorous proof, with every axiom laid bare, has definitely evolved over the centuries. It's a fascinating look at how mathematics itself develops.
So wrapping up then, the method of exhaustion was this truly ingenious Greek technique.
A logical tool using approximation by simpler shapes, usually polygons.
Combined with that powerful proof by contradiction, the double reductio ad absurdum.
To rigorously figure out tricky areas and volumes.
And it really stands as this critical early step, this ancient route exploring limit concepts way before formal calculus emerged.
Absolutely. So hopefully you now have a clearer picture of how these incredibly smart ancient thinkers laid that groundwork, achieving amazing results with the tools they had.
It really gives you an appreciation for their ingenuity and the depth of their logical reasoning.
It does. And it leaves us with a thought. This core idea, approximating the complex with the simple, it hasn't gone away, has it? Think about computer simulations, numerical methods, engineering models.
Right, we still break down complex problems into manageable pieces, even with all our advanced math.
Exactly. So maybe the provocative thought to leave you with is, what other ancient ways of thinking, perhaps overlooked, might still hold surprising power or relevance for tackling the complex challenges we face today?